Our next speaker is Professor J.M. White of the University of Texas. He received his Kendall Award in 1990, which is this year. And his talk at the time was Photochemistry of Surfaces. And this time it is the surface chemistry of electronic materials. Professor White. I'll give you the 5 minutes time.
Okay. So I'll speak loud so the whole of Washington can hear. It's a pleasure to speak to a full house, and especially a pleasure to be the newest of the Kendall Award laureates, to have the opportunity to speak today. I was curious when I looked at the program why I got stuffed in between Sommerjai and Yates, but it turns out that if your name doesn't come at the end of the alphabet, you've never worked on a single crystal. That's not quite right, but I was going to advise the awards committee to please start looking for people around the A's, B's, and C's for the next single crystal guy that gets into this business. I'm interested in looking at the future, and that's what I want to really focus my remarks on this morning. If you ask yourself, well, why is surface chemistry so interesting? I once, as a graduate student, heard Herb Gutowski at the University of Illinois respond to a question about why is that interesting. He said, it's interesting to me, therefore it's interesting, but I think there's another reason why surface and interface science will continue to be extremely important and very interesting for almost any kind of system that you can name. And that comes from the simple notion that two phases or more phases communicate, talk to each other through the interfaces that connect them. There's a sense in which that same kind of thinking works amongst those of us who are part of the human race, and that's what I'm encouraging the people in this room and particularly the leadership, the Colloid and Surface Science Division, to do. That is to cross and connect those present disciplines that seem a little disconnected and bring them in to the fold, so to speak. Let me give you some examples. In my abstract, I said chemistry was the forgotten discipline of electronic materials. I said that because after reviewing over the last years what's been going on in that field, I became convinced of that. But just yesterday, there was a symposium next door on MOCVD. That's a really good sign that chemists of a variety of kinds, including gas phase, surface, whatever name you want to put in front of the word chemist, are participating in that. I'm pleased that Randy Creighton, one of my former students now at Sandia, gave a superb talk on things that happen on top of gallium arsenide with trimethyl gallium. Then there's beyond the area of electronic materials, we've got some work going on in this division in tribology. I hope that continues. But there are other areas, you know, corrosion, ceramics, explosives, thin films, dynamics, as we talked about in the last talk. It's interesting what happens when you sort of turn your graduate students loose. I have a loose graduate student this summer at Sandia. Greg Poirier, turns out, is working on electron dynamics on a femtosecond time scale, which I know absolutely nothing about, but I know it's the right time scale for some very interesting things to go on at surfaces and interfaces. There hasn't been much said in our remarks about the future with regard to theory. I think John Yates at our meeting last night, our dinner, mentioned theory. I think that's really a future for Colloid and Surface Science Division, and I hope that you can construct symposia that bring together people from the traditional physics, material science, and chemistry communities on that subject. There are two variety of kinds of theory, just as there are a variety of kinds of experiments, and I wouldn't want to leave out the simulation business. I remember 15 years ago when I was doing simple gas phase A plus BC reactions, how enlightening was to me to find out what the light, heavy, heavy collision means when you do a trajectory calculation. If you're a hydrogen atom, you'll do all kinds of wild things. So it's not a simple collision. And a lot of our ideas, the kinds of things that Gabor mentioned, will be illuminated, in my opinion, when we are able to do better and better simulations of surface processes. As an academic person, I'm always interested in the subject of where the students are going to come from in the next 10, 15 years. And because of that interest, I wanted to say a couple of things. You know you're getting old when the son of one of your former almost students, not quite, comes to work for you in your laboratory. Chris Worley, the son of Dave Worley, up here on the front row, is a junior at the University of Texas at Austin. He's in my lab now. So that's one place to get new students. You get your and that's happened twice to me in the last year. So the second generation's coming through. But on a more serious note, I think it's important for us to examine where the next generation of students is really coming from. I've taken on the task. I think I should have my head examined sometimes for doing so. Taken on the task of sitting on the Committee for Professional Training of the American Chemical Society. Now, I don't think I can get surface chemistry in there as an option, but we have just put materials chemistry in as an option. I guarantee you that you can get surface chemistry embedded nicely in advanced courses, and as long as I'm sitting on that committee, if you're willing to develop such a course and put it in your undergraduate curriculum, I'll see to it that it gets, I'll do my best to see to it that it gets through the curriculum. Art Adamson has a new edition of his book out. We need more of that. We need new problems in PChem text, for example. Right? When you talk about thermo, let's stop talking about just single phase gas laws. Let's put some surfaces right up at the front. I think that's a serious problem. Getting the notion that there's more to life than gases, liquids, and solids into the curriculum fairly early. Another issue that I think is really important, I worry a lot about, is where all the money is going to come from. If I told you that come October 1st, what do you think the budget situation in this town is going to be? I should speak real loud now. What would you guess? My guess is that we'll have Graham-Rudman. My guess is we'll have Graham-Rudman for a short while. That's my best hope. But if I told you that the House bill of the National Science Foundation budget right now has a 14% increase, would you cheer? Or is it too early? It's probably too early, right? If I told you the Senate hasn't done anything about this at this point, and they probably would do something about it in the next month, would you do anything about it? My point is that over the past several years, I've learned that, at least in Texas, the congressmen and senators, when you go to them and gripe about spending money on foolish things, they say, "Why don't you come tell us? You know what's really important." I remember going to the representative from our district in Austin complaining about targeting money on issues that hadn't been peer reviewed. He said, "Look, you didn't provide the money. That's the Congress's responsibility." Now, you may not like that point of view, but that's exactly right. The point is that as a group in this country, we need to do, as individuals, in my opinion, we need to be informed and argue for what we think is the appropriate level of support for longer-term budgets. So we have 3 weeks at this juncture to tell our senators, look, keep that NSF budget up there where it belongs. I think those budgetary issues, those student issues, and the issues of the future with regard to the subject matter of our discipline are things that ought to take up some of our time. Now, I wanted to compliment this division on its willingness to take people like me who never did any surface chemistry as a graduate student under their wings. And I started out thinking that the world was more or less carbon monoxide on metals, but I've come some distance from that. And I'm pleased to show you the following kind of slide. Okay? I meant to fix this yesterday. This is an interesting molecule, and illustrates a point that I wanted to make about what it takes to move forward, in my opinion, with regard to some of the future. This is a molecule. You'll look in the middle there, you'll see aluminum and nitrogen. Around the outside, you'll see silicon and carbon. And the question is, can you make a mixed aluminum, nitrogen, silicon, carbon containing film that's sensible out of that molecule? Now, I haven't the foggiest idea how to make that molecule. And as far as I know, you can't buy it from an Aldrich catalog. And you can't get a cylinder of it. So where do you get it? Well, this molecule was made by Bob Payne at the University of New Mexico, and through a collaborative project involving Tom Meyer at Sandia National Lab, Terry Mikulski at Sandia National Lab, Bob Payne, and myself. We've been able to dose that molecule on an oxide surface, silica, to get an infrared spectrum of it, to look at the thermal desorption products of it, and to assure ourselves that we actually deposited through decomposition some aluminum on that surface. This is a preliminary just statement of how complex a molecule you can really deal with, and deal with successfully. If I ask you to heat that molecule, imagine it's sitting on a silica surface, and you heat it up, what do you think the products will be? Would you ever make aluminum nitride-like species? Would you ever make silicon carbide-like species? Well, the answer is most of the chemistry involves a recombination of two of those trimethyl silyl groups to make a dimer of those, if you want, hexamethyl disilane. There's a lot of ammonia that comes off. For sure, you can leave aluminum behind. So, at this point, we don't know a lot about that. What we know is that we can successfully handle it, and we can do the traditional parts of surface science on it. That required the collaboration. That's my point. That a lot of things that you can look at doing these days almost always require collaboration with people who have skills that you don't have, at least that I don't have. The chemistry of electronic materials. I think this is a really important issue for surface chemistry and for materials chemistry. Here's a molecule that you can't buy. It's a cyclic molecule containing gallium and arsenic, some tertiary butyl groups. It's not drawn to scale, just schematically. This molecule is built by Richard Jones and Alan Cowley in our department at the University of Texas at Austin. Alan Cowley, of course, has spent his professional career in the main group of the periodic table. Richard Jones is one of these green thumb guys who can, like gardeners, make all kinds of molecules with the drop of a hat. The point is, you can ask yourself, would that molecule be a sensible or decent precursor to gallium arsenide? Or if it isn't, what could you do to the structure around the outside? Could you change the hydrogen on the arsenic? Could you change the tertiary butyl groups on the galliums into something that would be chemically interesting from the point of view of leaving groups? The next step, of course, is to try to do some surface science on that. What you do is you get an ex-catalysis guy like John Eckert interested in this problem. He's somewhere between this little diagram, which represents chemisorption and desorption, which is my area, and he's somewhere between that and thin film growth, which would be the next panel. The point is that we can't do this second experiment unless we've got the first guys in line, and they've got to be willing to stay with us long enough to tinker around with those ligands up there based on what we see leaving as C or being deposited as B. What I can tell you about that molecule is that under ultra-high vacuum conditions, you can make a gallium arsenide thin film that has no more carbon in it than you can find by secondary ion mass spectrometry on commercial gallium arsenide. The single crystal character of the resulting thin film that you make by thermal decomposition of that molecule, the single crystal character is not so good as detected by the optical properties of that gallium arsenide thin film, but we're really encouraged by that. But you also need some good people. Cindy Flores, postdoc, and Xiaoyang Zhou, graduate student in my research group. But there's another step that you get when you can connect up with Randy Creighton. Randy Creighton belongs somewhere in this gap, in my opinion, between the second and third panels. And you can, Randy, a former student from my group, now working at Sandia, is really, in my opinion, the leader in this area. And then you hire Russ Dupuy into the electrical engineering department. And there's a guy who's an electrical engineer, but he knows about chemistry. When you go there and talk to him, you have to learn a little bit about electrical engineering, which is incumbent on me, but if I tell him what a tertiary butyl group is, he knows, and that's about all the organic chemistry I know. So Jones and Callan have to teach me up the top. I have to teach Dupuy, and then it runs back and forth. The point is that there's an this is an enormously complicated problem. Chemistry has an important role to play, and in my opinion, that's a way of the future. What do we know about some of these simpler molecules? Here's a common, today being studied widely, precursor, or you can put ethyl groups on the gallium. And we've looked at that briefly on silicon 100 and gallium arsenide 100 surfaces. A lot of this work, I'll steal a couple of slides from Randy Creighton. My part of this is going to emphasize just one or two techniques that haven't been talked about, at least at this particular meeting. So, just to get you oriented a little bit, you would pyrolyze trimethyl gallium in the gas phase into 3 methyl groups, and a gallium, you'd end up with 60 kilocalories per mole as a requirement for what's going on. So I put this in here just to stress that we've got to get more than just surface chemistry involved. We need some really good gas phase chemists involved. In my own group, I can probably handle that problem reasonably well since I was trained there, but that's an important aspect of what's going on in the gas phase. Here's just a kind of schematic. Look at this second slide, or the second half of this. Trimethyl gallium absorbed on silicon looks to us like it breaks off 2 methyl groups, puts those methyls on surrounding silicons. Those methyl groups are very, very stable. Mostly what they do is what I've shown at the bottom. Mostly you can make some gallium with some carbon hooked onto it. You can make some silicon with some carbon hooked onto it. So if you want to make gallium arsenide on top of silicon without an intervening layer of some kind, this is not a good molecule to go with. So what kind of evidence do we have for these kinds of species? Well, a variety of things. This is a very busy slide, and it's a bit too complicated, but it's the kind of complexity that you get if you dose trimethyl gallium on silicon 100 and you do static secondary ion mass spectrometry on it. If you look at these panels, they go from 10 AMU to 100 AMU, and as you come up from the bottom, you're going from low temperatures, 115 Kelvin, up to high temperatures. So let's just look at the bottom one first, and then compare that to the top one, and look at the right-hand side. Over on the right-hand side, there's a dimethyl gallium plus signal. Look at what happens. I've colored that red, 115 strong, 200 Kelvin strong, 350 Kelvin much weaker, 680 Kelvin nothing. Okay, so somewhere in that temperature range, that particular species disappeared. There's another peak there around the 80s in circles in green. It's much weaker, monomethyl gallium plus. Look at the gallium signal, around just above 67. Starts weak, gets strong, and then disappears after 850 Kelvin. Silicon peak, Si2 plus, in between. In the red at the top, it's strongest. Over on the left-hand side, clear over on the left, mass 15. Real good diagnostic for methyl groups and how they're hanging around. So they start out and actually grow a little bit. Okay, so there's some change that's occurring between 115 and 200 Kelvin that causes the CH3 plus signal to rise. The interpretation of that is that between 115 and 200 Kelvin, you've broken some carbon gallium bonds and you've made some silicon carbon bonds, and the cross section for the desorption of mass 15 species as ionic species is stronger after that occurs. And then that goes away as a function of temperature. So from SIMS, you can see that there's good evidence for some fairly strong CH3 groups hanging in here to the region around 600 Kelvin. Here's a temperature program version of that particular problem. What you see here is TPD, temperature programmed desorption, and static SIMS in a temperature program mode superimposed. In temperature programmed desorption, the only molecules we see desorbing are hydrogen, up there around above 8, but just below 863 Kelvin on this particular scale, and the parent molecule, which is desorbing way down here around 115 Kelvin. There's a little disagreement between this work and some of the very nice work that Rich Maisels has done about the presence of methane. We've not been able to find methane desorbing under our conditions. Now you see this SiCH3 plus signal. See, it hangs in here. It's relatively stable. Signal to noise is not particularly good, but you can certainly tell that it hangs in there to well above 500 Kelvin and is gone, coincident with the desorption of this hydrogen. So there's a kind of kinetic picture that you get in a transient mode by doing the combination of this static SIMS experiment with the temperature programmed desorption. Here's a gallium and the methyl groups. Look, the methyl groups are hanging right in there, right along with the SiCH3+. And the gallium signal rises and then falls. Okay, it's fairly constant until those methyl groups leave. And the cross-section for that rises. And we always have cross-section problems in SIMS. Qualitatively, you can get the picture here about what's happening when. Now look over to the left, there's a blue curve there that has the dimethyl gallium plus signal multiplied by a factor of 2. Look, it's gone by room temperature. So we would say that above room temperature, you have no longer any dimethyl gallium species on the surface. Here's the temperature programmed desorption that summarizes what we see. We see the parent molecule at low temperatures. We see hydrogen at high temperatures. And under our conditions, essentially everything that absorbs decomposes. Let me just close with one other slide. I wanted to just show you what trimethyl gallium on gallium arsenide does. This is Randy Creighton's slide. It makes an important point that's more or less consistent with these observations. What this slide shows you is if you put trimethyl gallium on gallium arsenide and heat it up, you see a huge methane signal, you think, until you look at it more carefully. And you see that mass 15, 14, 13, and 12, they're at the lower part of the curves, the lower 4 curves, and the upper curve is mass 16. There's no way that that can be methane. Very little methane desorbing here. Then you ask yourself, could that be methyl groups? And the answer is mostly methyl groups desorbing. So methyl groups really do like to desorb as methyl groups from these monomethyl gallium species that we and others believe are important in the decomposition of trimethyl gallium. Let me close by just thanking you, the committee again, for honoring me with the Kendall Award this past year, and I guess this year technically, and it's a pleasure to be here. Thank you for your attention.